Okay, good morning. Welcome to
FamilyMath1153.
Math 1153. So today we're reviewing the proof that we did yesterday because I felt like I made a few bad decisions in that project yesterday, and you had some really good ideas that we didn't get to explore all the way. So we have this proof attributed to Tom Apostol, who was a professor at Caltech.
Yeah.
And it's a proof that the square root of 2 is irrational. So how does this proof work, since we talked about it yesterday?
Okay, so
you have a pencil. If you want to write anything on here, you certainly can.
we start with a isosceles right triangle, and we assume that it has integer side lengths. So the two legs are integers, and the hypotenuse is also an integer.
Okay, and so what does that have to do with the square root of 2?
That proves that, well, since this triangle is an isosceles right triangle, it has to be in the ratio of 1, 1, root 2.
Mm-hmm.
And that means that we can multiply root 2 by a number to make it rational, so that root 2 must also be rational.
Okay, great.
Or,
Yeah, if root 2 is equal to, let's say, m over n, then if I have a 1, 1, root 2, which would be 1, 1, m over n,
yep.
then I would also have an n, n, m
Okay, yeah.
triangle. Okay, good. And then what does this picture show?
That you can, no matter what the side lengths of this triangle are, you can create a smaller triangle with the same property as the big triangle is.
And what was that property?
That they're integer sides. So these two small sides are integers, and then this length is also an integer.
Okay, so if I start out with an isosceles right triangle with integer side lengths, I can actually create a smaller one with integer side lengths.
Yep.
And what problem does that create?
Because it sort of creates a problem that you can always, it just keeps going on forever, because with this triangle you can also do the same thing.
Okay.
And if you start with finite side length, eventually you're going to basically run out of integers, and
That's
you
right.
can't go
Right.
any farther.
That's exactly right. You're going to get smaller and smaller and smaller, but they always have to have integer side lengths, and that
Yep.
can't happen. And how does the proof work?
So let's see, we can start with, so maybe labeling the sides.
Okay.
You can call these sides A, B, and this is also B. And I guess we do have to prove that.
Okay, so why are these two lengths the same?
We can draw in a line here if we want. And see that these two triangles are congruent because they share two sides and a right angle.
Okay.
They share this one line side.
All right, nice. So we get that these two line segments are the same.
Yep. And then
Okay.
I guess we have to sort of create some relationships between, like, using the Pythagorean theorem. Since this side is also A,
Mm-hmm.
we can say that maybe A plus B equals the square root of 2A squared.
Oh yeah, let's not go through the computation. We'll just go through the geometry. So we know these two sides are the same.
Yeah.
All right. There's a third side that's the same.
This one here.
Okay. Why? Why is that the same?
We sort of assume we sort of created this length at the start?
Not quite. That length was created by sort of folding this, or well, actually folding is what we're going to do next. Sort of drawing this one over and having a side length here and here.
Oh, okay.
So why is this side length here the same as this side length?
So we have to show that the triangles are similar, and we can do that by showing that they by angle, 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 because this is a right angle here.
Okay.
And the small triangle shares a 45-degree angle with the large triangle, and so that means this angle also has to be 45.
Okay. So that shows that this side length with the double dash, this one with the double dash, and this one with the double dash are all the same.
Yep.
But it doesn't show that they're integers. So why are they integers? If I started with a big triangle like this where all the side lengths were integers, why are these side lengths integers now, the small ones?
Well, let's see. Did it have something to do with the fact that we could create Pythagorean relationships with this, or just from the geometry?
It's just from the geometry, actually. Think about the procedure we went through for creating this picture. What did we do?
We by assuming that A is an integer side length, and that this side is an integer side length, we took off A from it, and since the integers are closed, that means the remainder also has to be an integer.
Okay, so that shows that this side length is an integer.
Yeah. And then all of the other side lengths are equal to it.
Yeah. So now we have that this side is an integer. So how do we know that the hypotenuse of our smaller triangle is an integer?
This triangle is similar to the large triangle.
Not quite. It's not that they're similar.
No.
There's a different reason that this hypotenuse here is an integer.
But we also, since B is an integer, we also took it off from A, and that means the remainder has to be an integer.
Yeah, there you go. That's the whole proof. So you show that these three side lengths are the same, that this is an integer, and that's an integer, which means that is an integer.
Yep.
So pretty cool. It's a good proof. Now we're going to explore the same proof through folding.